So this is not 100% true. That uncertainty principle is only related to or only introduced in quantum mechanics. Because if you think about it, um, when we are talking about frequency and time in classical physics, um, whenever you have a sine wave of specific frequency, the specific frequency is like a single frequency. So imagine the response, let's say on x-axis there is frequency and y-axis there is amplitude. Then on x-axis there is only one value of frequency for that entire sine wave. So if there is one single sine wave, then there is only a single frequency for that sine wave, but it is spread out in complete time space. So whenever there is a singular frequency, the time spread is minus infinity to plus infinity. But whenever there is a short time interval, then it is composed of multiple frequencies. Like what I am saying right now, let's say if I'm saying a word or even a letter that has multiple frequencies in it, it's not a single frequency. So, but I'm saying it for a short time interval. So when you make time as a short interval, when you make time small, basically the frequency spread increases, and when you make frequency spread small, the time spread increases. And this is purely classical. You cannot have time and frequency uh, precisely same as a singular frequency or singular time, because they are just Fourier transforms of each other. So time and frequency wise, if you want to go from one domain to another, it is completely classical phenomena. I actually sent a video on Telegram, and that video actually demonstrates this very nicely. That there is also classical, because in starting point, like to think about uncertainty principle, I think we don't talk about it much in classical physics because we don't term it as uncertainty principle. But I think time and frequency domain, which are Fourier transforms of each other, um, they give you a nice introduction, like a nice idea about how this principle also is valid in classical. I guess in quantum mechanics it comes because we extend this time and frequency Fourier transform concept to energy and time uncertainty and momentum and space uncertainty. So these two uncertainty principles actually are inherently quantum mechanical. They don't exist in classical physics. But the time and frequency one is like wave mechanics has it's inbuilt in the wave mechanics, which is classical wave mechanics. So this is like a nice point to remember, that it's not completely random quantum mechanical thing, which is uncertain principle. Time and frequency thing is already involves that uncertain principle.
One point I would like to add to this is that when you talk about uncertainty principle in quantum mechanics, inherently you talk about measurement and simultaneous measurement. Okay. Now, there is a generalized formula. If there are two observables, and if you want to apply uncertainty principle, then they follow a particular relation in which you estimate the uncertainty into a particular observable, and then you do a product with another observable, right? So observables do have their corresponding operators, right? For example, position and momentum operators. Operators are there, observables are there. But when you talk about energy and time uncertainty principle, then this logic fails. You cannot apply that formula. right? This is just an addition. You can continue. Yeah.
Yeah, right. Actually, this is how you can go from classical physics to quantum mechanics, because there are like multiple pathways which help you bridge that gap, like go from one formalism to another. And one very good way, I think, is going from Poisson brackets, which is classical thing, to commutators in quantum mechanics, because both of them describe like very similar things. And it's very easy to go to make transition from classical to quantum mechanics if we are going from Poisson brackets to commutators. And I think that has the uncertainty principle inbuilt in that, because when you take commutator of any two variables, any two observables, then if that commutator is zero, that means, or Poisson bracket is zero, that means you can measure the two things simultaneously. So if you are measuring anything, if you are measuring energy of a specific system, then to make a very precise measurement of that energy, you need to do that measurement for a long amount of time, for a large amount of time. And similarly, if you are taking a pulse measurement, which is like you are measuring the time, exact time, then you need a lot of uncertainty into your energy. Similarly, it's like if you want to measure a position of a particle very precisely, then you need to hit it with something, right? In order for us to know what's the position of that object. Because, like, how do we know position of any object in the real world, right? It's just sun rays come in our eyes, like they hit our eyes. They first hit the object and then they come back to our eyes. So it's like it just happens by reflection, and then our eyes absorb it, and then that's how we detect that okay, this object is at this much distance and what's its position. So this is the same thing that happens whenever we do measurements, that we are incidenting photons, which is photons are particles of light. We are incidenting photons or any other particles for that matter on the object or on the system that we want to measure the position of. um, and when we do that, we get the position of that uh, system or that object. But what happens is in the process, we hit that object, right? So whenever we hit that object gets displaced. So then now we know the position of that object, but it has some momentum as well. So in order to measure position of that object, we need to disturb that system. In fact, to make any measurement on using any observable, what do you mean by observable in quantum mechanics? It's just something, some property of the system that you are measuring, and that same observable, like that same property, if you want to write down mathematically, then that is called as the operator in quantum mechanics. That you are operating on a wave function. And what do you mean by wave function in quantum mechanics? It's just something that represents your system, something that represents the state of your system. Uh, Basically, if you have a system that has a specific amount of energy, total energy of that system, if you write down the total energy of that system, then by writing down total energy, we can solve Schrodinger's time independent equation, which gives us, which is basically Hamiltonian operated on psi is energy times psi. Um, and there is, yeah, so if you solve this equation, or if you basically, if you know energy, total energy of that system, then you are able to find out that, okay, what are the different possible states? If we measure the energy of the system, what are the possibilities that we can get? Like, it's like if we measure, if we are saying that what are the possible outcomes for a dice if we throw a dice? So there are only six possible outcomes, right? So one of them has to come out. So it's like if we throw a dice, it will be either 1, 2, 3, 4, 5, 6. It won't be 7. It won't be anything else, because it can't be. If you toss a coin, there has to be heads or tails. It can't be anything else. So similarly, for any system, if you know the total energy of that system, there has to be specific energy states in quantum mechanics. That's how we formulate everything, that if you know the total energy of that system, then you should be able to figure out what are all the possible energy states for that system that are possible when we measure the system, and when we take any measurement. Basically, if we are measuring momentum, then there are specific like states or specific uh, amplitudes or specific values for those momentum that are possible. If you are measuring positions, there are specific position values that are possible. If you are measuring energies, there are specific energies that are possible. If time, so it's like all the measurements have specific um, possibilities in quantum mechanics, especially because classically, if we talk about systems, then they are they are mostly continuous. We can consider them as continuous systems. And in continuous systems, if you have, let's say, a free particle that has a kinetic energy, it's not under any potential. So potential energy is zero. So your total energy is basically your kinetic energy. If that is the case, if that is like a free particle, then for a free particle, any amount of energy is possible, right? So it can be 1, it can be 2, it can be 2.5, it can be 0.1, it can be any real number, basically. But that is not possible whenever you make the system bound. Whenever you have a potential energy for a system in which the system is bound, then you're only allowed a certain energy values, which is the basis behind quantum mechanics and which is the basis behind quantization. So whenever we talk about like classical mechanics and quantum mechanics, I think these are the distinctions that we can start with. Is there is inherent there is intrinsic property of quantization in quantum mechanics, which is basically telling you that each energy there is a minimum amount of energy uh, that is possible to change in your system, and there are specific number of states for that energy. That's where I think quantum mechanics starts, because there are like, of course, we all know in quantum mechanics there are like two basic equations of Schrodinger, which is time dependent Schrodinger's equation and time independent Schrodinger's equation. Um, Time independent Schrodinger's equation is basically you have if you know the form of energy, let's say a free particle just has kinetic energy, so it's half mv square, right? So then if you know the total energy, then you can find out what are the possible energy states. If you know, let's say it's a harmonic oscillator, then harmonic oscillator, you know that total energy is just kinetic energy plus potential energy, and potential energy is half kx square because force is minus kx, and from that if you take potential energy. So basically, if you know your system, then you can find out the energy eigenvalues of that system, which is basically how many um, different number of energy levels are there in that system. Uh, that's what that's what gives you the first thing, which is time independent Schrödinger's equation. If you solve that, you will get the total energy values. And now what you want to know is if you start in one of those energy states, if you are in the initial wave function, is psi naught, let's say. If you start in that state, how will you time evolve? What's your time evolution of that system? If you let the system evolve in time, if you keep watching the system, or like if you let the system propagate in time, then if you observe it after a certain amount of time, where will that system be in terms of energies? Because how much energy I have determines what I will do in my actions. It's very philosophical. It's like that's the basis of Schrodinger's equation, that if you know the energy of that system, you can predict the behavior of that system. It's like it also connects to entropy later, that energy is related to your entropy disorder and everything, because it's like how your energy is distributed in your system determines how your system is going to behave micro, like in the micro region, um, like atomic physics wise, nuclear physics wise, or material science wise, any regime from starting from micro structures to macro physics, like all the stars and everything. all of them can be written can in terms of just energies, total energies. And if you know the total energy of your system, you can predict the behavior of that system in time. How will it behave in time, in future, or how it has behaved in the past? You can predict everything, and it all revolves around the energy of that system. So that's like the motivation to start from energy, and why we talk about energies always, because Newton started, I think, um, like to solve any system, or like to understand any system. Earlier physicists, I think, used to talk about forces, but yeah, I think this is like classical mechanics motivation, that everyone starts from forces, but then we go to energies because energies are easier to deal with. They are more fundamental as well, and they are scalars as opposed to forces, which are vectors. So yeah, and that's why we learned, even in classical mechanics, we have learned this formalism of Newton's mechanics. Then we learned Lagrangian. Then we learned Hamiltonian mechanics. These are all classical things. Uh, Even classically, you can solve everything in terms of energy, starting from energy, and derive all the equations of motion in classical physics. In quantum mechanics, I think we do the exact same thing. It's just that we start from the Hamiltonian itself and derive everything in terms of these two Schrodinger's equations. And then there are applications of Schrodinger's equations, which give you like all the detailed descriptions of your system and perturbative regimes. And there are like applications. Like I think Griffith gives you like a good idea about quantum mechanics. But anyway, it's like a I just gave a short introduction about like quantum mechanics. But I guess now everyone is here, so then we can like dive into the actual lecture. Should we? Can we? Is it okay? Sir, is it okay if I start?
Yes, yes, please continue.
Okay. In that case, I'll start. Yeah. So in any case, if you want to interrupt, anyone wants to interrupt in between for questions, you can unmute yourself and then just ask me, or even put questions in the chat if you don't want to speak out. Um, and yeah, at any point of the lecture, if you don't understand anything, or if you want me to spend more time on some concept, then please let me know so that I can. Because I have to take your feedback so that I know what's the pace for the lecture, what's the correct pace for the lecture, and what's the background. Because I don't know exactly everyone's background, whatever they have learned so far. So it would be good to uh, like kind of get feedback. Also, since the last lecture, some people approached for like with ideas and what to do in the lecture, and what are the things they want to focus more in the lectures. So I really appreciate that. Please, like I'm available on Telegram and also email. So please contact me if you have any ideas for this lecture series, and if you have any feedback as well on whatever lectures have been presented already, and whatever lectures are planned ahead. So, and if you have any, of course, if you have any doubts about the lectures or the lecture notes or any of the formalism, yeah, uh, please contact me. Okay. Anyway, so actually in today's lecture, I just wanted to talk about a few things to lay the foundation. Let me just. Okay. So why are we actually talking about like I have sent lecture notes in the group, but why are we starting with, or why are we talking about harmonic oscillators or two-level systems or resonances? Because I think these things are the most fundamental things, especially in atomic and molecular physics, because these form like the basis of like all the theories that we are going to learn in this lecture. these lectures and also all the derivations that we are going to do, they have inbuilt these three concepts, and all the research also, even all the research that is happening around the world still uses these concepts. So, so this week I was at a conference and still they were like most of the conference was just talking about resonances. So resonances is like the first thing that you should know whenever you're starting atomic physics. So, um, so what exactly is a resonance? Um, it is basically if you drive any system, then if you basically impart energy to any system, then and the system starts oscillating, it will oscillate depending on how much energy you provide. So it's like if you consider harmonic oscillator, and then uh, let's consider harmonic oscillator. So in harmonic oscillator, classically, you have this potential, right? This potential, which is potential is half kx square, where k is, I guess, omega square. You have this potential. This is x, and this is potential energy. And then you have a minima for that potential. This energy, potential energy, is described by just half kx square, which is just it's a mathematical function. Um, so if you have this parabola, just x square, it's if you plot y is equal to x square, you'll get this graph. So this graph is like just this is just mathematics till now. So what is the physics of this system? Then basically any system. What are the examples of oscillators in real world? Um, there is a spring mass system that we are always talking about in physics since like high school. There is a if there is a rigid support and you have a spring and there is a mass associated with that spring at the end of the spring, and then if you pull it or push it, it is going to come the other way because of the restoring force. And that is basically it for the oscillations, like oscillators. That that model, that spring mass system model, is like the fundamental model in physics. You can describe uh, any system in terms of just that oscillator. Why? Because if you solve that oscillator, if you solve this system, which is just half kx square potential energy, so the total energy of that system, total energy is kinetic energy plus potential energy, which is just half mv square plus half m omega square x square. If you solve this system, which is basically if you put, this is your Hamiltonian now, if you put this Hamiltonian, I mean, this is not the form that you put in generally, but if classically, if you consider this is classical, then if you put this same energy form, but just in quantum mechanics, if you put, so this is classical form of the Hamiltonian. Similarly, we write this is the quantum form of Hamiltonian. It gives the exact same information, but just in terms of two different operators, which are A and A dagger operators. So I will explain this, but let's understand first why we have started with this. Because classically, if you solve this system, classically, if you solve this, everyone is familiar with this, like this expression, right? So that I won't explain much about this. Let's say this is equation one and this is equation two. I will explain everything about equation two, but um, let me just know in chat if you are familiar with equation one. I think everyone will be familiar with equation one because it's just I have written total energy of the harmonic oscillator. And okay. So if we, so this can be our starting point of the discussion, because I need to know where to start. So then this first equation one will be the starting point. So let me just minimize this. Okay. So if this is the starting point, then if you solve the differential equation classically, you get a final answer in terms of sines and cosines. So let's say the solution of this equation is sin x. So it is a harmonic uh, solution, which is like the solution can also be cos x. The solution can also be e to the power ix. Again, this is Fourier series cos x plus I sin x. So any solution which is periodic in time, um, which is like a single frequency. So this is one of the solutions. This can be one of the solutions of this equation, which is the equation of motion for that harmonic oscillator system. So what we got to know eventually is in classical systems, um, the solution of harmonic oscillator is sines and cosines, which is like harmonic solution. So this very fact makes harmonic oscillators very important in physics. Why? Because if you know in mathematics there is a theorem called Fourier theorem. So there are two parts in Fourier. So Fourier has given like contributed in mainly into different mathematical theorems. One of them is Fourier series, and second is Fourier transform. So what is Fourier series? If you want to understand just philosophically what is Fourier series, then any function, any mathematical function f of x can be written in terms of sines and cosines. Let's say a sin x plus b cos x plus blah blah blah. All the combinations of sines and cosines. So this statement is what gives like that's the statement for Fourier series. That Fourier series tells you that any mathematical function, let's say 1D function, any mathematical function can be described in terms of sines and cosines. So essentially that becomes your basis now. So sines and cosines now become your basis for your entire formalism. What do I mean by basis is if you have, let's say, a 3D space, three-dimensional space, then generally what do we use as our basis in Cartesian system? Generally we use I hat, j hat, k hat, which is just x cap, y cap, and z cap. These are the three directions, right? X cap, y cap, and z cap. So if we want to talk about three-dimensional space, then we have to talk about a basis in terms of this basis. That okay, if I am at a specific position in three-dimensional space, if I am at a coordinate, let's say 5, 3, 2, this information here gives you entire picture of where your position is, because we are talking in terms of basis. That I x component is the value of x component is 5, so I have to travel 5 amount, like 5 magnitude in one direction. Then I have to go 3 magnitude in another direction, and then I have to go 2 magnitude in z direction to reach, starting from origin to reach where I am right now. So why I'm emphasizing on this is because this forms the formalism of our basis. Because in quantum mechanics, it is very important to know what basis we are in, because we do change of basis all the time. It's like I think you guys must have done this already, but I will just reiterate that if you want to explain everything that happens in three-dimensional space, you can do it in Cartesian coordinates, you can do it in cylindrical coordinates, you can do it in spherical coordinates. Change of coordinates does not change the physics. And that's I think what Einstein said in his relativity principle and everything, that if you do change a frame, your physics doesn't change, just the equation of motion and then the form, that how it's written, that changes. So uh, remember this, that change of basis. I'll write this statement down because this is a very important statement, even though it feels very trivial, but it is very important statement in both quantum mechanics and classical mechanics, but especially quantum mechanics, that change of basis does not change the physics. And what do we call change of basis in quantum mechanical language is projection onto a different basis. So remember this part, this will come later, let's say, but um, this is very important, that you're projecting from. So if you have information about a system in Cartesian coordinates, let's say, then you can do change of coordinates by projecting that basis, Cartesian basis, on, let's say, spherical basis, and then you will get information in terms of the spherical basis. But the information remains the same, the physics remains the same, the understanding of the system remains the same, but just that now your frame of reference or your method of understanding or the basis basically changes. So in linear algebra, it's everything. I think comes from linear algebra directly. That this is just mathematical formulation. That linear algebra, you can define your vector space first, and then once you define the vector space, once you define your basis, then you start explaining about your system. Then you attribute, okay, in this basis, what is the first component, what is the second component, what's the third component. You can have n number of components. So, okay, how does all this relate to harmonic oscillators? Why I was telling you about the Fourier series is because Fourier series basically tells you that the basis of sines and cosines, which is the harmonic basis, that basis is sufficient for us to explain everything that happens in any mathematical function that is 1D, let's say. So that is so powerful. That statement is so powerful that um, any function f of x can be written in terms of sine and cosines, basically harmonic. What this means is, how it relates to physics is, we already saw that, we already know that simple harmonic oscillator solution is just e to the power ix or sin x or cos x, depending on the boundary conditions. So basically, this harmonic oscillator basis should be sufficient for us to a certain extent to explain anything, like any system, in terms of just harmonic basis. So then if we choose this basis as our basis, then we will try to explain all the systems that are there in uh, atomic physics, like systems such as two-level system, which is like atom, then harmonic oscillator, which is light, which is like light. I'll explain why two-level system is like an atom, why harmonic oscillator is like light. But what we want to do in this course is see the interaction between the atom and light atom interaction. That's the aim of this course, right? So then what's the correct basis, or what's the formalism that we want to understand this with, is in terms of harmonic oscillators. That's like this entire motivation for like 15-20 minutes was to motivate that how important this harmonic oscillator system is. This formalism will help us understand both atomic physics and light separately and light atom interactions in terms of just this harmonic basis. So that's why this system is very important. So now you can understand this system again in terms of something else. So if you have, this is also an important statement that if you have continuous energy levels, then that is for a free particle. So potential energy is zero. But for a bound particle, now you have discrete energy states. So whenever you make, if the atom is, if any system is free to move anywhere, then it's not under any potential energy. There is no external potential that is applied uh, under under that potential's influence. Our system is not moving. So our system is moving freely. Then for a free system, you get continuous energy levels. But remember that for a bound system, you get discrete energy levels. Because you're making the system bound, now you're restricting the system to have certain specific energy levels in that system. So if you do, if you think about now, and whenever we are thinking about discrete systems, um, okay, so let me tell you how the transition happens from discrete to continuous. So it's like if you have, let's say, this harmonic oscillator potential, and if you are making this potential weaker and weaker, if you are making the boundaries lesser and like flatter and flatter, slowly it will go to a v equal to 0 line, which is basically what we mean by free particle. So if you have a potential, you can always decrease the intensity of that potential, the magnitude of that potential, and then it will slowly approach the classic, it will slowly approach the free particle limit. Free particle limit is when you have continuous energy levels, and bound particles is when you have discrete energy levels. More bound the particles are, more discrete the energy levels become, and equidistance the energy levels become. So now if you think about harmonic oscillator in that regime, then basically if you have a system that is bound, you can, for energy levels that are close to ground state, which is like the lowest energy state, you can have this model of harmonic oscillator to explain that system which is bound. Let's say a system is bound. Let's say if we have a spring. So then if we move that spring like this, then it vibrates with a certain amplitude. Then if you excite that system further, it will increase the amplitude of its vibration. But this is not limited, right? You can increase the amplitude up to minus infinity to plus infinity. It's not restricted at all. So remember this, that if you want to excite this system, which is like a bound system, which is vibrating. Okay, and why am I imagining this system as a vibration? Is because if you imagine, let's say, a harmonic oscillator, which is a spring mass system, then whenever you impart some energy on it, whenever you compress or whenever you extend that spring, it goes on doing this vibration in the real world. So similarly, any system. So this was a mechanical oscillator, right? So the spring mass system describes a mechanical oscillator. If you want to think about electrical oscillators, then you have LC circuits. In LC circuits also, there are oscillations happening, like electrical oscillations. So that is, LC circuit is an example of electrical oscillators. Then you have, in atomic physics also, you can have oscillators. In quantum optics as well, you can have oscillators. In that case, then light is your oscillator. In atomic physics, atom is your oscillator. So you can basically understand all these systems in terms of just this oscillation. But if we are thinking about a classical harmonic oscillator, it doesn't have bounds on its amplitude. So if we have a system and it's oscillating in this direction, and this is like the amplitude of its oscillation, then if you provide energy to the system, there are no bounds to the system. So you can increase the amplitude from minus infinity to plus infinity. You can increase it n number of times, and also there is a zero. So for the amplitude, the lower limit is also zero, exact zero. So if you don't oscillate the system, if you don't disturb the spring mass system, then it is staying at the same position, right? So it's not oscillating. So the amplitude of the oscillation is zero. So completely zero, it stands still. And so the lower limit is zero, and the higher limit is infinity, because you can excite the system to any amount of excitation, and it will still excite. Of course, in the real world, you can imagine a spring mass system. You won't be able to extend that spring to infinity, right? There will be some bound. So in real system, there will be bound to this oscillation. But that's a different topic. That is a topic when we will talk about two-level systems. But for an ideal, imagine ideal classical harmonic oscillator. So let's make another page. So for a system where ideal classical harmonic oscillator, first you have no bounds to excitation. Secondly, the lowest energy state is equal to zero. So at the lowest, if you don't excite the system, it will have zero energy. Then you have n levels. So if you have now, okay, so now we were talking about ideal classical harmonic oscillator. So now what will happen in terms of, if we talk about now quantum harmonic oscillator. In quantum harmonic oscillator, now you will have discrete energy states. So I think one of the lecture notes that I sent has this diagram. So even these, so it's like an n is equal to 1, first energy level, second energy level, third energy level, and so on. So basically, if the particle is bound, this is basically our same system, but now we are considering that the energy levels are discrete because the particle is bound, and because we are now talking about quantum mechanics. And because like I said, whenever we go from classical physics to quantum physics, now we have to remember that there are only certain number of allowed energy values for that system. So it cannot take any arbitrary energy value. There are only certain number of values, certain number of energy values that are possible for the system to take. So actually the quantumness of the system comes from this quantization of energy, that you're now restricted, basically. You cannot have any energy that you want. You're as a system, you cannot go into any energy state possible. There are certain number of energy states that are your basis, that is the basis of your system, and you're only allowed to go to those energy values. So if you solve this harmonic oscillator, then you will get this energy value structure, which is just n plus 1 by 2 h bar omega, and for each n, you will get a specific energy. So now, if we want to understand, so this is quantum harmonic oscillator. So what was the difference between classical and quantum harmonic oscillator is basically the quantization, which is now your lowest energy state also doesn't have, so E0 is not zero now. Because if you put n as zero, then still you have some energy, which is your 0 point energy. So even the lowest energy state of your system has some energy. That is the difference between quantum harmonic oscillator and classical harmonic oscillator. That firstly, you have discrete energy states, that is even there in um, basic like quantum mechanics, that each particle, which is each system which is bound, will have discrete energy states. You are only allowed a specific amount of, and like you are only allowed specific values of energy, which again, which comes also in Bohr's atomic model, right? That for electron that is revolving around the nucleus, which is an atom basically. So that electron can be only in certain energy states. Though those are quantized energy states. It cannot randomly be in any orbit. Those are called orbits in the earlier part of this theory of atomic physics. So even in that system is a bound system, right? So electron is bound to the nucleus. So whenever you have a bound system, you will have discrete energy states. I think this statement is also important, very important. So bound systems. Maybe I'm repeating this a lot, but bound system is discrete energy. So now if you consider this model and you want to understand this model in terms of A and A dagger. So what are A and A daggers? So uh, what's the motivation behind this A and A daggers? Okay, let me tell you what philosophically A and A dagger, what do they do? If we are in the n is equal to 1 energy level, so I didn't draw the n equal to 0. Okay. So if you are in n equal to 0 energy level, and if you want to go up by 1, so if you want to go from n equal to 0 to n equal to 1 energy level, then what do you do quantum mechanically is, let's say you operate, so this is an operator. A dagger is an operator. You operate this on psi 0, and what this does is takes you to another energy state, which is psi 1, which corresponds to this. N equal to 0 wave function was psi 0. So if you are in this state, you are described by psi 0 wave. If you are in n equal to 1 state, you are described by psi 1 wave function, because each state has a corresponding psi associated with it, which is our basis basically. So it's like I was explaining, in three-dimensional space, you have a basis vectors, which are x cap, y cap, and z cap. Similarly, for this system, which is harmonic oscillator, quantum harmonic oscillator, you will have now basis, which is psi 0, psi 1, psi 2, psi 3. So your complete basis will be in terms of psi 0 plus psi 1 plus psi 2 dot 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 dot, all the energy levels, and they extend to infinity because there is no bound to this. So these all energy levels together, these all wave functions together, or these all the states together describe the basis for this system. So like I'm deliberately using basis term a lot, because this term will come, this term will be important whenever we are talking about change of basis, which we are definitely going to do in our main derivation of atom light interaction. So this is very important. So okay, so what do A dagger and A do? These are called as annihilation and creation operators. So it's like you're creating energy. You're I know in physics you can't create and destroy energy, but I think formalism wise you should understand it like this: that annihilation operator and creation operators are those operators, if you act on a system or if you act on a state of the system, then it takes you one ladder up, one step up in that system. So your first energy state was psi 0, which corresponded to E0 energy. So first you had E0. So okay, consider that you are an atom, and let's say you are in this energy state. And if you want to go from n equal to 0 to n equal to 1, you need an operator that will operate on you. Basically, you need some external thing that will operate on you and take you from n equal to 0 to n equal to 1. That operation is mathematically described by a dagger operating on psi 0 gives you some energy plus psi 1. So there will be some constant here plus psi 1. So basically, you have gone from this energy, like the first energy, to the second energy. Now, if you want to come back, then you operate annihilation operator on it. Then you will get back with some amplitude to the original state. So basically, A and A dagger are they are formally called as ladder operators. Ladder operators. If you want to explain everything about quantum harmonic oscillator, you can explain in terms of ladder operators. And if you want to write your Hamiltonian in terms of ladder operators, then it is just H is A dagger A plus half H bar omega, where basically A dagger A is just number operator. Number operator, what do you mean by number operator? Is if you operate number operator on a wave function, okay. Let's see, there is a question in chat. Can you let us know when a system can be treated as a harmonic oscillator problem and when it can be treated as a simple potential well problem? As we see in nuclear physics for the shell model, there were various proposals for the potential part. Oh, I think in general, I have seen people using harmonic approximation, which is treating the potential as harmonic whenever you are near the minimum. So whenever you are near the minimum, you can treat the potential as a harmonic potential. Otherwise, you'd have to take like the exact form. So if you are close to, like, let's say the minimum energy state, then I think in most of the cases you can treat it as a harmonic potential, and you can treat it as half kx square, because I think this comes from Taylor series expansion basically, that whenever you are near a maxima or a minima, your potential is parabolic. So like this shape is always there whenever you are talking about uh, like a parabola. So then, and the parabola, whenever you are talking about a parabola, let me just, sorry, there was notification sounds. Ignore those. Sorry for that. So whenever you are near the minima of any potential, then I think harmonic oscillator approximation or harmonic potentials are valid to take. But in other systems, then if you are not near the minima, then I think this approximation fails, unless your system is totally like harmonic. So I think that's when you can use the harmonic oscillator potential, and in other cases you can't. I think that's the explanation. But if Nitin sir has some other insights, then he can add.
Yes, you are
He can add.
correct. Actually, what Sachit is getting confused is with the full potential and the potential of the problem you are interested in.
Mhm.
So what Soumitra is saying is that suppose you have a system, it may have any form of full potential. Okay. But if the system is at equilibrium, and if the system is being perturbed and you are now interested in that dynamics, so you need not expand, you'll be typically doing a Taylor series about that equilibrium position and then neglecting the higher order terms, right? This is what you do in small oscillations. So you can have a system. See, the full potential of the problem can be anything. But if you are
Mhm.
interested in the dynamics near the equilibrium, what is happening, then you can Taylor expand it and then do the thing. So it is different. There is a distinction between solving for full potential and analyzing and concentrating on the dynamics near equilibrium, right? So near equilibrium, you are concentrating on this linearity. Okay. So this is Soumitra is quite right in explaining the things. Okay, you can continue. Yeah.
Yeah, so I think then the main motivation is because each system, irrespective of what that system is, it will eventually tend towards an equilibrium, right? So then all the systems in the universe will always tend towards an equilibrium, which is like the minimum energy possible for that system. That's like the fundamental of physics, that
Provided the system is stable. provided you are at a point where the system is stable, right? If
Yes.
it is unstable system, then it will not come back. That's the
Yes.
rider in there. Yeah.
Yes. And it's like you also have this in thermodynamics, you have this law that entropy always maximizes and the total energy of the system always minimizes. So then I think that is applicable in terms of thinking that, okay, every system is trying to equilibrate all the time, so that distribute the energy in such a way that, okay, they will reach the equilibrium. So that's why whenever you're talking about, like Sir said, whenever you're talking about a situation where you are near equilibrium, which should be the case for any system that is stable, then you can talk in terms of harmonic oscillator potential. So, okay, so we were talking about number operators. So whenever what do I want to say about number operators is basically if you act a number operator on that on a specific wave function, then you're acting a dagger a on psi. What that will do is first it will annihilate, so it will go to n minus 1. So this acting on this will go give you n to n minus 1. And then this acting on this will give you n minus 1 going to n. So basically you will get back the same thing. So you'll get your n, which gives you now, you'll get, if you started with, let's say, psi equal to 1, you will get back to psi equal to 1. But you will, what you will get is the number of particles that are present in that system, in that state. So let's say psi1 is the first energy state, then n1 will give you the number of particles in that state. That's why we call it a number operator. And that's why the classical expression that we have always seen, which is n plus 1 by 2, or even harmonic oscillator, you have seen this expression. This expression is exactly same as this expression. And we are going to use this red expression a lot. So make sure that you understand this expression. Um, I know I have not derived it very classically and thoroughly, but I don't think uh, I want to spend a lot of time in derivation of this Hamiltonian because it is fairly straightforward, and I don't think you need to know a lot. This should be our starting point. But if you want to know, if you want to derive it for yourself, then you're welcome to do it. It is like the formalism in terms of annihilation and creation operators is really well explained in many of the textbooks, including Griffiths of quantum mechanics. So then, if you want to go over that, if you want to review that, you are welcome to do that. The only important thing that I wanted to mention was this is the solution. Like these are the energy levels, right? So then actually this is energy levels. So energy levels in a harmonic oscillators, how to go from that to a Hamiltonian is these two things convey the exact same thing. And now you have to understand in terms of annihilation and creation operators. Annihilation operator acting on a state will annihilate by 1. It will decrease your state by 1 with an amplitude, and the creation operator will increase your states by 1. So it's like you're going up by 1 or coming down by 1. And why we are talking about going up by 1, going down by 1 in terms of discrete things is because now we are talking about a bound state, and the bound state has discrete energy states. That's why we have to go up like +1, +2, +3, or -1, -2, -3. Like that. So that's the motivation to talk in terms of discrete bound particles, in terms of the discrete energy states. So that's why we are using this formalism, and that's why this formalism is very useful to convey this. The annihilation creation operator formalism is the best, I think, to explain everything in terms of quantum harmonic oscillators. So remember this Hamiltonian. this Hamiltonian we are going to use a lot, but whenever I'm talking about quantum harmonic oscillator or harmonic oscillator in general, imagine that I'm talking about just this expression. And like I said, everything comes from energy. So in quantum mechanics, we will always start from a Hamiltonian. We will start from a Hamiltonian, then we will write. Let me write the recipe. So it's like the recipe for all problems in description of a system. First is write down the Hamiltonian's form. Like it it is here, a dagger a plus half h bar omega. Later, I may even ignore this part. I will may even ignore this part because those are just constants, right? We don't like the essential physics is like the important thing here is the Hamiltonian is of the form a dagger a. In physics, we as we go in the more classified or more like detailed topics, more specialized topics, we tend to ignore the constants because the constants don't tell us much. Of course, when we are doing experiments, we have to take them into account. We have to match exact values to our precise experiments so that theory matches with the experiments. But whenever we are talking about the formalism, whenever we are talking about the derivations, the constants don't contribute a lot while explaining everything about the system. We can understand everything in terms of just the operators. And what are the operators? Operators are the observables. What are the observables? Observables are some methods like the properties of the system, which we can directly observe when we do experiments on that system. So that's why A and A dagger are operators. Hamiltonian is what gives the total energy of the system. And once we know the total energy of the system, what we will do is we will solve this equation, which is Schrodinger's time independent equation. We will solve this equation. This equation will give us the states, which are basically energy. The actual name is energy eigenstates. It's just a fancy way of saying that there are only certain number of energy levels that are allowed for the system, and we will only if we solve the system, then we will get that as the final value because I think in linear algebra, if you have a matrix and you find, let's say, n cross n matrix, you find the eigenvalues of the system by any method. There are a lot of methods to find the eigenvalues of the system. So you have n values, which are the eigenvalues of this matrix. And then you get eigenvectors, which is the basis of this matrix. So this matrix you can write in terms of summation of all these vectors, summation or multiplication of all these vectors. And then you can basically describe all the physics by writing this entire thing, the system Hamiltonian, in your basis states. So this is I know this is very basic introductory thing, but I want to clear this out in like first few lectures so that later we will dive like deeper into these topics and these will be important to us. So that's why the recipe is for any system, first write down the energy, the form of energy, the form of your Hamiltonian. That Hamiltonian will tell you that, okay, these are the terms that are important to us. These are the operators that are important to us. This is what is happening in the system. Once you have the Hamiltonian form, just solve this Schrodinger's equation, time independent equation. You will get the energy eigenstates of the system. So what are all the energy? What are all the energy levels that are there in the system? What are all the possible energy levels that are there in the system? And then once you have the energy eigenvalues of the system, you know that okay, there are only these number of energy states in that system. Let's say if we are solving hydrogen atom, then hydrogen atom, we get solution in terms of NLM, all the quantum numbers. So we basically know that, okay, there are these possible orbits that are there in the hydrogen atom whenever we solve it for the first time. And n equal to 1, n equal to 2, these are the only allowed energy eigenvalues. What that means is basically that is the basis now in which we will talk about the hydrogen atom. And we will understand everything about hydrogen atom just by talking in terms of the energies of that basis. And the third thing we will do is we will understand the time evolution of the system. And for the time evolution, we just have this equation, which is now Schrodinger's time dependent equation. We will solve this equation and get the evolution of the system, time evolution of the system, which basically gives you the behavior of our system. So first we find out the energy eigenvalues, and then we get the behavior of the system as we let it time evolve. So that for getting the time evolution, we need to solve this time dependent Schrodinger's equation. But anyway, so this is going to be the recipe, and I think we are not even going to do the step 3. I think understanding the system and understanding its energy eigenvalues, basically understanding the Hamiltonian, is what is the most important thing in theory. In experiments, then you need energy eigenvalues, then you need everything. But anyway, the last thing I wanted to explain. Okay, there is a question. If there are only certain chosen energy states that are allowed, then how do we explain metastable states in the laser system? Since the metastable states is not naturally possible, I guess. I don't think that metastable states are something very weird. They are possible, but it's just that you need to be in a basis where metastable states are explained. Because whenever you are in the original basis,
Soumitra, yeah. See, energy levels are there. When you talk about metastability, you are talking about decay from that state, right? So energy levels are there. Or for example, if you take a one-dimensional potential, right? Take one-dimensional potential in which you have two minima. One is the global minima, and other minima is situated higher in energy. Now your system lowest energy possible is the lowest minima, it is global minima. But if your system land up in a higher minima, then you call it as metastable state. It is not the exact minimum that is possible. So when the question actually you seems to have a concept, misconception regarding metastable states in laser system. It is being said because the system exists actually. That energy state exists, but you are talking it in terms of decay from that system. Okay, so which can be explained in terms of this global minima and maximum. So,
yes.
but if you solve the problem, those states will exist. Yeah,
It's not
continue, please.
it's not coming out out of nowhere. It's like when we solve the system, the energy levels, we can predict that, okay, there is going to be this metastable state there. So it's not a surprise to us whenever we see a metastable state. I think we will talk about metastable states, and we will talk about when we talk about lasers, which should be maybe next lecture or after that, because um, whatever I am explaining today is about harmonic oscillators in two-level systems. We will come to metastable states, and I will explain in much more detail. But the short answer is that metastable states to come as the solution of our, if we solve this Schrodinger's equation. They are not like some surprise element that we need to add, but actually we need, like, the surprise element that we need to add is the spontaneous decay, is the spontaneous emission. But I will come back to that later, because spontaneous emission is not explained by Schrodinger's equation. It is not something that comes out. It is something that we put by hand, because that is something that is a non-linear effect, and we are only talking about right now linear effects. But anyway, uh, other than these three things, like writing down the Hamiltonian and solving time independent equation and solving time dependent equation, the only thing that we have not talked about maybe is populations, because if you know that, let's say, the electron is there in, let's say, hydrogen atom, you know that electron is going to be, you know that hydrogen atom uh, will have one electron always. If it is not excited, it will have one electron. Even if it is excited, I mean, if it's not ionized, it will have one electron. So stable hydrogen atom has one electron. So you know that there is going to be one electron, which means that the probability of finding that electron in the hydrogen atom whenever we do the measurement, finding that electron in one of the energy eigenstates is 1. So the total probability is 1. So which again means that it is the summation of all the states, the probabilities, the probability of that electron being in the first state, which is the ground state, plus the probability of it being in the first excited state, plus the probability of being in the second excited state. If you add up all these probabilities, then the addition has to be 1, because we know for sure that the electron is there in one of those states. So this will always be the case. Maybe not always. We will talk about that later. But for linear systems, for simpler systems, it is always the case that probabilities are always conserved. I mean, in the case, the one that I mentioned like 2 seconds back, where it is not true, it is when system is coupled to a bath, which is like system is coupled to an environment. But we will not talk about that right now. We'll talk about that later. So when you are just considering the closed system, let's say, if we have a system where only the energy exchange is possible and no matter exchange is possible, then if we are considering just a hydrogen atom, then we know for sure that electron is there, which means that we know for sure that the probability of finding that electron in one of those orbits is 100%. So if we add all the possible probabilities, then we'll get 1, which means basically the population of electron in all all the states of all the bound states will be different, and we will measure that probability, or we will measure that population. So populations of each level is what we will measure, and the populations are, if you write in terms of psi0 plus psi1 plus psi2 plus blah blah blah, if you have n such states, then if you denote this by A0, A1, A2, blah, 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 AN. Like I said, everything is associated with the amplitude. And now the last thing missing from our explanation is the populations, which is populations are just the squares of this amplitude. So if you want to know what's the probability, and actually if you want to be exact, then you need to normalize this with respect to all the populations. So the population of being in one of these levels is basically what will the square of that coefficient will tell you, and these are eigenvalues. Like if you solve in terms of if you solve that Hamiltonian, you will get that those eigenvalues, eigenvalues and eigenvectors. From these two, which is what we got from solving the time independent equation. If we see this, and if we then solve the Schrodinger's time dependent equation, then we will see that how the populations change in different levels. Basically, this is called as system dynamics. That if you start in a ground state, or if you start in the first excited state, or if you start in any state, then how that system will evolve. What that means is how the energy will be distributed. What that means is how the populations in specific levels will change when you apply some energy, or when you apply some perturbation on the system. So this is like the quick review. Maybe it was not quick, but it was necessary. So this is the review of quantum mechanics in terms of harmonic oscillators. So this is roughly the entire picture that we will need to know whenever we will talk about quantum harmonic oscillators. And in general, in quantum mechanics, we will talk about solving problems in this formalism itself. So this is like the recipe. I will once the lecture is over, I will send this lecture note as well in the Telegram group and also in the classroom, so that in case you want to refer to it again, or if you want to see what happened in the lecture, you can go through it. Maybe so. I mean, the handwriting is not great, but it's just that it will help you recollect whatever is done in the lecture. But before we conclude, I wanted to say one last thing, because actually I wanted to explain many of the things in this lecture, but I think due to time constraints, we will have this lecture in two different. Okay, so someone is raising hand. So okay, if you have any doubt, if you can unmute yourself. Ajay Kumar, I think. Unmute
Yes,
yourself and
sir.
ask.
Yeah, sir. Sir, when we are talking about population, are we talking about the population of the particular state or the whole system?
Yes, particular state. Population of the whole system is going to be one.
Yeah,
When I say that population, when I am talking about, let's say, if we have just one particle, then we are talking about that one particle can be in any of these states. There can also be the case that we have multiple particles. So if you have multiple particles, then you also talk about, okay, how many particles are in this state, or how many particles are in this state. But whenever I'm talking about one particle with n number of states, then by populations, what I mean is what is the probability of that particle being in one of, let's say, first state, second state. So let's say if it's 30% probable to be in the first. So it's like I'm talking about a coin toss. In coin toss, there is a 50% probability that it will come out as head, or 50% probability it will come out as tails. When I talk about populations, it is basically I'm saying that zero point 0.5 population is in heads and zero point 0.5 population is in tails. Similarly, in harmonic oscillators, if there are n number of levels, then when I'm talking about populations, it's like what is the probability of that particle being in one of these states?
Soumitra, uh, see, this concept of expectation value and this thing. So you can prepare a quantum system in as a superposition of different eigenstates, right? Suppose xi is a1 xi1 plus a2 xi2.
Mhm,
Suppose then and if you are making a measurement, if you are
mhm,
making a measurement, then a1 star, I mean a1 mod a1 square times with that probability results will come up, right?
Yes, yes,
And finding the second state, finding the particle or the system, rather system in the second eigenstate will be mod of a2 square. This is one thing, right?
yes,
Now you can have an assembly of system, which ultimately in density matrix formulation you will be doing. You will be considering ensemble, I mean identical system, but they will be in different quantum state, right? It may be a collection of hydrogen atom.
yes,
So you this distinction will be clear later on as the course progresses. What actually we mean by population, right? Whether the
yes,
system is being prepared as a superposition state, superposition of eigenstates, or it is an ensemble of identical system, right? A collection of hydrogen atoms, suppose, and then you are doing some experiment with it. So in that case, if you are dealing with a statistical ensemble, then
mhm,
the formulation of density matrix formulation of quantum mechanics will be helpful, and you will be able to talk about this thing. So there will be something called pure state and mixed state kind things like that. So but typically the way when you were taught quantum mechanics,
mhm,
you interpreted the concept of expectation value of an operator in
mhm,
terms of statistical measurement, right?
yes,
So these three concepts will become clear as we progress. So population, when we are using that word, it can be interpreted to have different connotations.
yep, yep.
Okay, sir. Thank you.
Yeah.
Sir, can you scroll down to the last equation once, the population wala?
Mhm.
This, yeah. So here you have represented population as the first state, the amplitude of the first state, right? Square of the amplitude of the first state. So if we are talking about population, it has to be the whole, the probability of the whole system. So is it represented as the linear combination of the other amplitude states?
No.
Like
Okay. So there are two ways to look at it. So if I am given a choice, let's say if I am given 10 rooms, right? So if I have 10 rooms, then I can, and if I am allowed to go in any of the rooms, and if you tell me that, okay, I can sit in any of the rooms, then I can literally sit in first room, then after some time open the door, sit in the other room, or if I am now considering myself as, which is what we do when we go from classical physics to quantum mechanics, is we now consider particles as waves. So then they can be distributed. So particles can be thought of as a collection of waves, and a wave can be thought in terms of particles. So that is where the distinction lies. So then we talk in terms of particles as collection of probability waves. So it is like now your particle, you know that your system has 10 number of states. So if your harmonic oscillator has 10 states, and you know that your particle is in that harmonic oscillator, one of the states, then you say that, okay, there can be two possibilities, that either it is in one of those 10 states, which is like n equal to 1 state, n equal to 2 state, or n equal to 3 state, or anything. Or it can be a superposition of those states, which is what Nitin sir was telling, that which it can be like a coherent state or like a superposition. It can be prepared as a mixture of many states together. But when we will superimpose, when we will do measurement on a specific level of that system, then we will get to know that, okay, what is the probability of us finding that particle in that specific level? So then the population become a specific about a specific energy level. So even if it is a superposition of many states, even if the presence of a particle is like a superposition of many of the states, you can, if you are measuring just one of those states, then you can superimpose that superposition onto a one state, and then you will find out that, okay, what was the probability of finding that particle initially when we did the measurement? What is the probability of finding the particle when we will measure just that one state? So even if it is even if it is prepared as like a single state, if so, it's let's say a particle starts at n equal to 2 energy state, then let's say we have prepared n equal to 2 energy state particle. Then if we measure n equal to 1, we will find that it is not there. So we will find zero probability. So then that means that it was prepared as n equal to 2. Now if we measure n equal to 2, we will find it 100% probability. But this is not always the case that we prepare the system is only one state. We can also prepare in superposition of all the states, because we think of particles in terms of waves, in particles in terms of probability waves, that this can be, it is possible to have it in uh, multiple different levels with different populations or different probabilities at the same time, which is what superposition is. Because in waves, you know that different waves can mix together, and there can be multiple waves contributing to the same point. The same thing happens in physics. It's just in quantum mechanics. It's just that now we are talking about probability waves, which is another representation of saying that the atom or the particle can be in any of the states, but there is a specific probability. If you measure, then you will find that there is a specific probability of finding that particle in a specific state. That's why if, for both cases, wherever, so like you said, there are two ways to prepare the system, one in a specific state or in a superposition. So, but even if you do either of these, still you can talk about probabilities in both cases. Does that answer your question, or uh,
yeah, it does. Actually, from what I understood, like is that कि अगर if you are measuring, if you are taking a measurement, then it constrained to the particular state, right?
yes?
Okay, thank you so much.
Okay, because whenever we are doing measurement, we are talking about a specific state of the system. So when we are doing measurement, we have to talk about the eigenstates of the system. That's why I said this specific concept of basis is important, because whenever we are talking about a system, we are talking only in terms of the basis of that system. And then what is the probability of being in that state? What is the energy of that state? So we are talking about specific states. But whenever we are not making a measurement, then the system can be in a superposition of all the states that is possible. So yeah, it boils down to actually measurement. So we will talk about measurements a little bit more. But final point, I think we are already kind of over time, though we started a little late. So um, what I wanted to convey in this lecture was, first, what we did was, uh, I think major part of this lecture, we have talked about like basic principles of quantum mechanics, how to talk about systems, and what is the recipe to solve the system using quantum formalism. So this was in this lecture mainly we had a quick review of quantum mechanical principles that any system, first you need to say what's the Hamiltonian for your system. Then for that Hamiltonian, you need to find out the energy eigenstates. And then from those energy eigenstates, we will find out from the time evolution, Schrodinger's equation, that how the system behaves when we say in the future, or we see in the past how it has behaved. So that's like the quick review of the quantum mechanical system. We also talked a lot about harmonic oscillator in this lecture, which is just this Hamiltonian. So I think next lecture I will talk a lot about two-level system. I will talk a lot about two-level systems, and this is also next lecture that we will connect these two, because the main point I want to convey whenever I am talking about harmonic oscillator and two-level systems is because we will talk about atom in terms of two-level system and harmonic oscillator. In any one of these formalism, we will talk about light in terms of harmonic oscillator or two-level system, any one of this formalism. But which formalism is useful when, in which situation we should consider which formalism? That is the important part. So when we are exciting the system, we can excite it with a lot of energy. We can excite it with very little energy. We can excite it for a long amount of time. We can excite it for a short amount of time. So there are different kind of experiments that we can do. So in which experiment, which formalism is useful, and how do we connect these formalisms, and how do we understand the system in different dynamics in different situations? That's what is important. So two-level system formalism is useful whenever you're considering nonlinear effects in your system, whenever you are considering like higher saturation limit, which is you are exciting with a lot of energy or for a longer amount of time, everything. So and in all the other cases, harmonic oscillator is useful. I will explain exactly which situations harmonic oscillator formalism is useful in atom light interaction, in exactly what situation two-level system formalism is useful. But first, in the next lecture, I will explain two-level systems. What are two-level systems? What are the characteristics of two-level systems? And we will learn the formalism in terms of, let me write down the Hamiltonian. It will be something like excited state plus energy of the ground state, like this. So we will talk about just two levels in the atom or in any particle, which is the ground state and the excited state. So we will use external energy and we will try to excite the system. But what is the two-level system formalism and how it is useful, or which systems can you apply that? That will come in the next lecture. So these two things I will discuss in the next lecture, and I want to spend some more time on this. But in the current lecture, we also talked about resonances, and we started with uncertainty principle, which is very important because in atomic physics, we are always talking about resonances. Whenever you're exciting an atom, when you're exciting an electron in a specific orbit, it will only excite from first orbit to third orbit, let's say, whenever you provide the exact energy for that system to go from the first state to the third state. So you need to be on resonant whenever you're going from first state to another state. So in order for light to interact with the atom or any system to interact with any other system, there has to be a resonance condition where these two things can interact. That's why resonances are very important, and that's why in atomic physics, resonances are studied like anything. And in harmonic oscillator as well, there is a resonance. So it's like in LC circuit, for example, there is an intrinsic frequency, which is if I think if I have not sent the lecture note, I will send, but this maybe just by memory, we know that this is like the harmonic, this is the frequency for LC circuit. So resonance frequency. So each like tuning fork experiments we have done a lot in our undergrad and other colleges. In those as well, there was a characteristic frequency for that tuning fork. So each object or each system actually has its own characteristic frequency of oscillation, and uh, that frequency, that frequency is very important because whenever you are driving the system, like whenever you're imparting the system with some energy externally, then if you match that energy with or match that frequency of excitation with the characteristic frequency, then you are at resonance. So, and at resonance, what happens is you get either the maximum output from the system or you get the minimum output. So there are two types of resonances that are possible. Okay. There is one doubt. You mentioned that in quantum optics, light acts as an oscillator. Is it somehow related to a change in oscillating EM fields as a response to change in electron cloud? Yes, it is. Yes, it is. It is not, actually speaking, it's not somehow related. It is exactly related to that. But so light can also be understood in terms of either harmonic oscillator or two-level systems. Why I say that? Because we know that light is electromagnetic wave, right? So it's changing electric field or changing magnetic field. That can be that formalism can describe how light is or what light is. So I think I sent even one uh, lecture PDF, like a short note on what is light. I also, I think, uploaded on Google Classroom. Let me know if you guys can't find it. But there was the motivation that light can be described as in terms of changing electric and magnetic fields, and light. So when I will explain light, light can be perfectly explained in terms of just this Hamiltonian, which is the harmonic oscillator Hamiltonian. So, and we can talk in terms of light as discrete energy levels, having discrete energy levels. So, because there is something in atomic physics which tells us that, okay, there are even vacuum energy levels, right? So then in vacuum, even if there is nothing, there is some energy, which means that the ground state of this harmonic oscillator is not zero now, which is not. So we talked about classical versus quantum harmonic oscillator, right? So the ground state of classical harmonic oscillator was zero energy, but it was not the case with quantum harmonic oscillator. So that's how you can relate like light with quantum harmonic oscillator, that the zero energy of light is also not zero, it is some finite energy. And then you can go up in steps, but I think we will talk about that more in the future lectures. But yes, light can be thought of as like an oscillator. And why it can be thought of as an oscillator? Because it's changing E and B fields. So we can think in terms of oscillations of electric fields or oscillations of magnetic fields to understand the light, um, or understand the photon basically. So because photon is the particle of light. So when you have an oscillation in the electric field, one photon is generated. When you have an oscillation in the magnetic field, one photon is generated, or something like that. So that can be the currency to talk about light, and that's why we talk in terms of discrete energy levels even in light. So oscillating electromagnetic fields, yes, that and the connection between the two, like how is, so since we say that light is oscillating electric magnetic field, right? And now we want to talk about how it interacts with the atom. But if you think about atom as well, it also has charges. What is an atom? It is a nucleus with positive charge and electron with negative charge. So electron cloud is the negative charge around the positive charged nucleus. So there is already a dipole in the so we can imagine atom as a dipole already. So now if you have an atom as a dipole, you can already see that there is a charge separation, and this charge separation can be excited using the light or using electric and magnetic fields, and that's how this formalism is going to develop, and that's how we are going to understand light atom interactions. Because I think I already also sent one lecture note which described atom as a dipole, which is like dipole means having two charges. So in that formalism, yes, we will use light as a changing electric and magnetic field, which is like a harmonic oscillator, and we will use atom as a two-level system. And this two-level system, like atom as a two-level system, is interacting with a light as a harmonic oscillator. This actually is going to be the formalism in which we will talk about light atom interaction. So yes, this question is valid, and I hope I answered the question, but yeah, this is kind of how we are going to discuss light as in terms of harmonic oscillator and atom in terms of two-level systems. But we will talk about that more in the next few lectures. But yeah, for now, that's the short answer that I will give. So yeah, so I was talking about resonances. So yeah, you need to match the intrinsic frequency of any oscillator with the drive frequency. The drive frequency is just the frequency that you are incidenting on the system. Uh, so basically the external energy or external potential that you're giving to the system. And omega naught is the intrinsic frequency of the system. For example, this F naught. Okay, another crucial thing actually is whenever I'm talking about omega, I'm talking in terms of angular frequencies. So F is frequency, which is hertz, which is basically 1/2. So how many oscillations occur in 1 second? That is the frequency. And whenever I'm talking about omega, it is 2 pi f. So whenever you see omega, you see it's the angular frequency. So whenever I write this symbol omega, I am always talking about angular frequency. And whenever I write f, I'm always talking about the singular frequency. So how many oscillations happen per second? So it's like if you have a harmonic oscillator and it is doing oscillations, how many oscillations happen per second is given by f. And what is the angular frequency of those oscillations? If you are talking about like oscillations in a atom or something, then that angular frequency is what I mean by omega. So actually in 11th, 12th, there is a really nice chapter that tells us the connection between simple harmonic oscillator and I think uniform circular motion. How these two things are connected. So if you remember this lecture, or if you recall this lecture, this is the exact same thing that we are talking about all the time in atomic and molecular physics. That how is simple harmonic oscillation related to the uniform circular motion? Because uniform circular motion is kind of the model that we are going to use in atoms in terms of when we are talking in terms of electrons moving around the nucleus. So that you can consider in terms of uniform circular motion. How is that connected to the spring? So it's just the I always remember I think trains wheel of the train analogy, that the shaft of the wheel, shaft of the wheels, like the shaft using which the wheels are connected, they I think do just this motion whenever the train is going by. And the shaft, if the shaft is doing this, then the wheels are doing this. So it's like uniform circular motion is directly connected with the simple harmonic oscillator picture, and both of them have exact same formalism, and you can talk in terms of simple harmonic oscillator and understand uniform circular motion, and you can talk about uniform circular motion and talk in terms of harmonic oscillators. So it's like connection between this 1D oscillation to the angular oscillations, so angular frequencies like rigid rotator, for example. So that's how I think we will form our entire picture, understanding all these phenomena first individually, and then making connections between them. So, but I think now I have taken like more than a few extra minutes, so I will just stop this lecture here. But in the next lecture also, we will talk about two-level systems, and we will connect basically two-level systems to the harmonic oscillator picture that we have learned today. And we will talk about resonances all the time throughout this course, because resonances are something that are very inherent in quantum mechanics and atomic physics, and those are the those are the phenomena that we use when we do experiments. To do all the spectroscopy experiments, to do anything, we actually use this phenomena. So actually, I will send this lecture to these lecture notes, but I don't think I have covered entire lecture which I wanted to cover today. So I will split this lecture into two lectures. Like I said, I think throughout this course, I will adjust to the pace, whichever pace is comfortable to the students. And let me know, like, again, at the start of the lecture, I also said that contact me on Telegram or on via email. Just send me a message. If the pace of the lecture is good for you, if you want more interactions in the lecture, if you want more lecture notes, if you want yeah, so please suggest, give feedback for whatever you think about the lecture. And but my basic point is, today we covered like three of these topics. We will cover the rest of the two topics, and we will connect all these systems. That will complete like the prerequisites that we need uh, before going to atom light interactions. So I wanted to cover this in like 2 or 3 lectures, and then move to the real derivation, which is for which we will use the textbooks that I have sent. So I think I would recommend that like go through, if you have not understood like some parts of today's lectures, then go through simple harmonic oscillator, go through quantum harmonic oscillator, understand that formalism from. There are many number of textbooks available. You can also use the two textbooks that I have given. Go through the lecture notes that I have sent. If you have any doubts in those, please ask. If you have any doubts in today's lecture, please ask. But I think for today, I will just stop here. But keep in mind, like today, I think we covered like the starting point was we talked about these three things. We also understood why Fourier series is important. How is Fourier series connected to oscillators? Why is oscillators the starting point where wherever we start in physics? Why we always talk about oscillators? Why how are continuous versus discrete energy states? What is classical? What is quantum about it? Um, how to go from classical physics to quantum physics? How to talk about quantum physics and its formalism when we were talking about a specific problem. What's the recipe to solve any system using quantum mechanics? Um, yeah, how to talk about it. And okay, we have not talked about this linear versus non-linear systems, but we will talk about it in the next lecture. So basically, two-level system is has some non-linearity in it, and harmonic oscillator, we can consider it as, if we consider it as simple classical harmonic oscillator, we will consider it as a linear system. So in the next lecture, I will explain that. But for today, I think this is what I wanted to explain, and I can, yeah. I mean, Nitin sir, if you want to explain something else, otherwise the lecture I can consider it as like we can conclude it.
Uh, yeah, it's fine. Yeah, you have written Professor Kitterly's
Yes,
lecture, first two lectures, because that course on AMO physics starts with resonances first and
yes,
resonance phenomenon, right? And
yes.
this is the typical way in which the course should progress. So those two lectures are very important actually.
Yeah, I
And
actually, whatever I
Utkarsh,
explained or whatever I am going to explain is completely inspired by those lectures by Wolfgang sir. And please watch them. Please watch the first two lectures. I think if you understand first two lectures, you don't even need to attend this introduction section, because this is like, he does phenomenal job, like much better than what I have done. So please watch those YouTube lectures.
okay, Utkarsh had raised the hand, and then we'll answer his query, and then we will wind up.
Okay. Okay.
Sir, I wanted to ask if the harmonic oscillator is the only potential that has evenly spaced eigenvalues, or can we design such potentials, or is it like something nature's inherent way? Like, why is the only square, like this square potentials equally spaced as discrete eigenvalues? Like, if we
Um,
consider any other potential,
mhm.
they don't have this discreteness in there? Like the energy levels aren't equally spaced.
I think, I mean, philosophically speaking, I don't know exact mathematics behind it, but philosophically speaking, because we are always talking about harmonic oscillator when we are near minima, when we are near the equilibrium, I think that's what makes the energy states equally spaced. But I think Nitin sir will explain it much better.
Well, I do not know any other potential at present which has this. We'll have to look into mathematics, because your question can be formulated in terms of a proposition, or in other way around it, you can ask that you are, see, when you are solving any this Schrodinger equation, you are basically, and you are given an Hamiltonian matrix, right? When do you say that you have solved the problem? You say that you have solved the problem once you know the spectrum of that um, Hamiltonian, right? So once you know all the eigenvalues, then you say that you have solved the problem, right? So your problem, your proposition can be said that, okay, you have given, you are given a spectrum for a system in which the eigenvalues are equally spaced. Now, what is the possible potentials and associated Hamiltonian? So mathematically speaking, your proposition can be written in this way. So will it be a uniqueness theorem that this is the case and it leads to a harmonic oscillator, right? So rigorous, we'll have to see actually in mathematics whether that theorem exists or not. So that will answer your question whether it is the unique, unique potential which is having this. Because at present I have not come across anything which is which has a spectrum which is this
Equally spaced.
spaced other than the simple harmonic oscillator.
Yes, sir. Thank
Yeah.
you, sir.
We'll see.
Regarding
But nice
Sachit's
question. Nice.
regarding Sachit's question, the lectures link. So, okay, I'll tell you two things. If you search Wolfgang Ketterle, um, Wolfgang Ketterle, atomic physics on YouTube, there is a lecture series by Wolfgang Ketterle, MIT lecture series on YouTube. And first two lectures of that series, I think it's like a 15-20 lecture series or something. So first two lectures of that series is what I'm talking about. I think I have shared the link for the same in the overview that I gave at the very start, like the before I even give the first lecture. I shared, like, I'm in the first lecture I actually went through that PDF where I show you different YouTube channels. Then in that maybe there is a link, but if there is not, I think just search for this Wolfgang Ketterle atomic physics in YouTube. First search link will be these lectures, and watch first two lectures of this. I don't think you will have a lot hard time finding this. Otherwise, I will share in the group. Yeah. Other than that, so even the next lecture will be based on just this introduction, and also inspired by the first two lectures of Wolfgang Ketterle. So if you guys get time, then please watch those. Otherwise, like, just read the lecture notes, or I will share maybe some other material. I will also share this notebook in which I have written in this lecture, and I will continue to write on just this notebook even in the next lecture. So that we finish everything that I wanted to explain. We can wind up by the way.
Yeah, yeah. So students can leave, and Soumitra, we will have a meeting with Krishna Sri.
Yeah. Okay.